Hello, my esteemed viewers. I welcome all of you for this first tutorial on the strength of materials. This is the beginning of series of tutorials on this fascinating subject. Strength of materials is variously called. Of course, this particular course has been variously called by several authors, but the traditional name has been strength of materials. Some call it as mechanics of materials, and some call it as mechanics of deformable bodies, and others do call it as mechanics of solids. Whatever the name be, the theory of mechanics of materials or strength of materials basically deals with capability of structures like beams, columns, shafts, cylinders and springs, etc. to carry the loads and their rigidity, their robustness and their stability. The structures need to be designed to resist the actual or probable loads. Here, design means proportioning the dimensions of a structure or a component. The designer of a structure should take care to see that the loads on the structure should not exceed the capability of the material out of which the structure, the component, maybe machine part is made. Also, the structure should not show too much of flexibility in terms of excessive deflection, excessive deformation, excessive splitting, excessive stretching, conjointly called as deformation. If any, it should vanish. Theory has it to say that if at all any deformation is there owing to the application of the load, it should vanish as soon as the loads that caused them are removed. Above all, a structure is expected to be durable with trouble-free long service span. This means we can quote few examples. The floor of a building should not sag too much. A cylinder, a pressure vessel should not burst. The shaft of a vehicle should not twist too much, unable to bear the twisting moment, unable to bear the applied load, unable to bear the internal pressure, as the case may be. A beam should not bend, deflect too much under the superimposed loads. A column should not buckle, unable to carry a load placed along its axis. Here, the floor, the beam, the column, the shaft, and the pressure vessel, and many more are called as structures or components or parts. And this terminology can be used interchangeably. Of course, the material out of which these components are made are rather important than the structures themselves. A floor should not sag too much, a beam is to bend, a column is to buckle, a shaft is to twist, and pressure vessel is to burst under the ultimate loading conditions, when the capability of the material out of which this floor, beam and column, shaft and pressure vessel has been made exceeds the capability, delimits under the action of exceedingly high loads. The sagging, bending, buckling, twisting and bursting are called as mechanisms or behaviors or deformation patterns. Therefore, interestingly, the strength of materials is also called as the mechanics of materials, because there is going to be mechanisms that is going to happen in terms of deformation, and it is also called as mechanics of deformable bodies. Therefore, in a nutshell, strength of materials exactly deals with determination of capabilities and deformations of various components or structures under the variety of loading conditions. And we will just explain a simple of the concept of a simple stress or direct stress. Let us assume that this is the component, a cylinder, a cylindrical column subjected to a load which is axial in nature. The load value is P. It may be in terms of kilonewtons, it may be in terms of meganewtons, it may be in terms of few newtons depending upon the situation. And the amount of load that a particular structure has to bear is context specific. If it is a column of a building, it has to resist huge amount of load, and if it is a column of a bridge, it has to take much more than few megatons, few megatons or mega newtons, kilonewtons, giganewtons. And immediately when a component is applied with a load over here axially, immediately a reaction will be developed and the system is in equilibrium as far as mechanics point of view is concerned. But anyway, in order to see the internal pains suffered by this particular component, we need to take a section. Let us say we have taken a section somewhere over here, and there comes the internal of this particular component. And here you can see the stresses emanating. The stresses comes just like a resistance opposing the applied force. And every point over this area of cross section participates in resisting the applied load, and this resistance comes in opposite sense of the applied load. Since every point over the area of cross section is involved while resisting the applied external force or external load, the resistance is developed internally in the material, and this material of the component, and it is called the stress. And here each and every point is made out of the material out of which the entire component is made. Therefore, when we express the stress, which is the internal resistance offered by the body against the applied load, it is the area is also considered into picture. Therefore, the stress is expressed as load divided by area of cross section. Of course, load is acting perpendicular to the area of cross section, and the cross section is taken by just running a sectional plane which runs orthogonally to the axis of this particular member. Therefore, stress is simply P divided by A, Newton per millimeter square. Newton for P and millimeter square for area. However, if we take a section, and of course this definition of simple stress as P by A holds good only in a particular condition, and that will be explained over here. And let us say if you have taken a section over here in the immediate proximity of the load, the stresses that is developed over here will be non-uniform, and this is due to proximity effects. Of course, there is a theorem depicting this as to when exactly the stress, the resistance offered internally by the body will be uniform in nature. Okay, and we have to move far away from the application of the load, and if we take a section somewhere over here, there is going to be stress concentration, and stress will be much more in the immediate vicinity of the load or beneath the load, and it will simply gets diluted as we move towards the edge. And this is the scenario that is being displayed over here. The stress is non-uniform because we have taken a section very near to the applied load, and in the proximity of the load, the stresses tend to be non-uniform. Stress remains to be uniform at a distance far away from the point of load of application. That means the equation sigma equal to P by A, that is load divided by area of cross section, is valid only if the stress is uniformly distributed over the cross section. That should happen, that will happen. And if we take a section somewhere over here, this is the component, and we have taken a section by owing to this particular section, we should feel as if the parts are getting separated, and this part is in equilibrium, this part is also in equilibrium, and in order to hold these two parts in equilibrium, and there will be stresses that is being developed, and this is the applied load and this is the stress that is being shown by the area of cross section. To realize this, the load should be axial, it should be acting along the axis, it should be centric, acting on the centroid of or center of gravity of this particular component along the axis, and the section should be a little far away from the application of the load or application point of the load. To realize this, the load should be axial, the section should be orthogonal, and it should be far away from the point of load. And we need to differentiate at this particular point of time. We need to differentiate as to what is pressure and what is stress, because both of them have something in common. That is, they are expressed as Newton per millimeter square or kg per meter square, whatever, because pressure is also the load acting over an area, surface area. And the pressure, in order to differentiate them, here is an explanation. Pressure at a point is eccentric, and this is the liquid, and we have considered a point somewhere at the depth, at a particular depth. And if you consider this particular point a particle within the fluid, of course exaggerated, and the pressure acts externally to every point over here. As far as stress is concerned, if we take a stressed body and if we take a point within the stressed body, stress at a point within a component is intrinsic. It acts inside the material, inside that particular point, inside the component. And if you consider any point within the fluid, the pressure is extrinsic, though the units are same. At a point, intensities of pressure is constant in all the directions. And if you take this point, this amount of pressure acting in multivarious direction, 360 degrees, is constant for a particular height, of course, for a particular height. Okay. And as far as stress is concerned, stress at a point within a body is not constant, and it varies. For example, sigma 3,3 is different from sigma 2,3, and the stress acting along x-axis is different in its magnitude, and y-axis it is different, and along z-axis also it is different. Stress at a point within a body is not constant in all the directions. An external pressure, if you apply an external pressure to a body or to an element, it can generate stress in a body, but converse cannot be realized. That means you cannot apply the stress and generate the external pressure, because stress is purely internal matter of a material. And if you consider a component, and if you apply the axial load, and if you take a section, using a sectional plane, and there is a development of a resisting area which is perpendicular to the axis of the member or perpendicular to the axial load, and this is the reaction that is being developed, because this particular body is to be kept in equilibrium. And if you take a section, that means the portion beneath the lower half of the portion, and you can see the stresses being developed opposing this particular force. And this stress is uniform because we have taken a section at a point which is farther away from the applied load. This is the resisting area, and this is the stress, and this is the applied load. Therefore, load is a cause, stress is an effect. How much stress for a load depends upon what material you are talking about. And therefore we have to devise the units of the stress. Basically, conventionally, the stress has a unit of a Pascal behind the honor of the scientist. Pascal is 1 Newton per meter square. And in order to have a feeling for this unit, you have to assume an area measuring 1 meter by 1 meter, and it is as good as placing an apple over here, and expecting some kind of a resistance. It becomes a too meek a quantity, too small a quantity. And in reality, the components will be subjected to huge amount of stress. So a Pascal means only this: keeping an apple or a weight equal to an apple, a load equal to an apple weight, and over an area measuring 1 meter by 1 meter. Therefore, in order to amplify this particular stress, which is the reality in real world problems, real world design problems, It is usually expressed as 1 megapascal. 1 megapascal is 1 pascal into 10 to the power of 6. That is 1 Newton per meter square into 10 to the power of 6. And when you convert this meter square into millimeter square, it becomes 1000 into 1000. 10 to the power of 6 will cancel away. And here what remains is millimeter square. Therefore, 1 megapascal is 1 Newton per millimeter square. 1 Newton per millimeter square is a great stress. Right. It is as good as placing one apple over an area measuring 1 millimeter by 1 millimeter. And it is also expressed in cases, in situations where stress is going to be huge. Usually stress will be expressed as gigapascal. Gigapascal is 1 pascal into 10 to the power of 9, which is 1 Newton per millimeter square into 10 to the power of 9. 1 Newton per millimeter square can be converted into Newton per millimeter square. Meter square can be converted into 1 Newton per millimeter square. 1000 into 1000. So 10 to the power of 6 will cancel away with 10 to the power of 9. What remains is 1 Newton per millimeter square into 10 to the power of 3, or 1 into 10 to the power of 3 Newton per millimeter square. Therefore 1 gigapascal is 1 megapascal into 10 to the power of 3. And to conclude, here is a person who is lifting the weight and he is not happy because he is getting compressed. And here is a person which is doing hang-ups, and the entire body will be in tension. The body is not happy. Therefore, in a lighter vein, stress may be viewed as a displeasure shown by the body internally due to external loading. This displeasure comes out in the form of resistance that pervades the entire cross-sectional area. So in this tutorial, my dear viewers, respected viewers, we have understood as to what strength of materials is, and on what issue the strength of materials will deal with, and what do we mean by the terminology stress, simple stress, normal stress, and how it is different from the pressure, which has stress and pressure has same kind of units, Newton per millimeter square or kg per meter square. This difference we found out, and the condition to call a simple stress a simple stress, a direct stress a direct stress, a normal stress a normal stress. The conditions are: 1, the load should be acting centrally on the centroid or over the axis. 2, the section should be taken at a perpendicularly to the longitudinal axis of a component, and it should be distant away. Then the stress will be uniform. So simple stress is a resistance offered by the material out of which the component is made to the external applied load. So this comes we come to the end of this session on strength of materials, which has explained only the very primitive things, very rudimentary things on strength of materials. And as we continue, we will explore this fascinating subject, okay, in a proficiently increasing manner, in the increasing order of proficiency. Until then, bye. And if you have liked this video, kindly subscribe to my channel. So bye till we come with the other tutorial.